Every moment, without our conscious awareness, a rhythmic symphony unfolds within our chest. The heart performs a cycle of contraction and relaxation that sustains life itself. This cardiac cycle is not just a mechanical sequence of events, it is a marvel of physiological coordination, timing, and precision. Good evening, one and all. This evening, we'll journey into the cardiac cycle not as passive observers, but as curious explorers. We'll decode how the atria and ventricles dance in synchrony, how valves orchestrate one-way flow, and how pressure gradients drive the movement of blood. By the end of this session, you won't just know the phases of the cardiac cycle, you'll understand how this elegant choreography keeps us alive, beat after beat. Before we dive into the mechanics of the cardiac cycle, it's essential to understand what makes cardiac muscle so uniquely suited for its lifelong task. Unlike skeletal or smooth muscle, cardiac muscle possesses a set of specialized properties that enable the heart to function with precision, endurance, and autonomy. Let's walk through these 5 key properties. Contractility, also known as inotropism, refers to the heart muscle's ability to contract forcefully. This is the fundamental power behind each heartbeat, propelling blood through the circulatory system. Autorhythmicity, or chronotropism, is the heart's remarkable ability to generate rhythmic impulses on its own, without external stimulation. This self-pacing nature allows the heart to beat continuously, even outside the body under certain conditions. Conductivity, or dromotropism, describes how electrical impulses travel through the heart muscle. This property ensures that the signal to contract spreads efficiently and in a coordinated manner, maintaining the rhythm and timing of the cardiac cycle. Relaxability, also called lusitropism, is the muscle's ability to relax after contraction. This phase is just as critical as contraction. It allows the chambers to refill with blood and prepare for the next beat. Excitability, or bathmotropism, is the heart's responsiveness to stimuli. It's the threshold at which cardiac cells react to an impulse, and it plays a vital role in maintaining proper rhythm and preventing arrhythmias. Each of these properties contributes to the heart's resilience and reliability. Together, they form the physiological foundation for the cardiac cycle, a cycle we'll explore in detail a little later. To understand how the heart beats in a coordinated and rhythmic manner, we must explore its internal electrical wiring, the cardiac conduction system. This system is the heart's own built-in pacemaker and signal distributor, ensuring that each contraction is precisely timed and synchronized. As we have already learnt in our earlier sessions, this entire sequence is reflected in the ECG waveform, a visual representation of the heart's electrical activity. Each peak and dip corresponds to a specific phase in this conduction pathway. Together, this system ensures that the heart doesn't just beat, it beats with purpose, precision, and perfect timing. It's a beautiful example of how structure and function are seamlessly integrated in physiology. Let's now shift our focus from the electrical coordination of the heart to its mechanical function, how it pumps blood through the lungs and the body in a continuous loop. The essence of the circulatory system is in 2 interconnected circuits, the pulmonary and systemic circulation. Blood from the upper and lower body returns to the right side of the heart, which then pumps it to the lungs for oxygenation. This is the pulmonary circulation, a low-pressure system designed for gas exchange. Once oxygenated, blood flows into the left side of the heart, which then propels it forcefully into the systemic circulation, reaching every tissue of the body, from the brain to the toes. This is the systemic circuit, a high-pressure system responsible for delivering oxygen and nutrients and collecting waste products. This elegant loop operates continuously, powered by the rhythmic contractions of the heart. It's a perfect example of how structure supports function, 2 sides of the heart, 2 circuits, 1 unified system sustaining life. As we move forward, keep this dual-circuit model in mind. It's central to understanding cardiac physiology, blood pressure regulation, and even clinical conditions like heart failure or pulmonary hypertension. Now that we've explored the heart's electrical coordination and its role in circulation, let's take a closer look at the actual pathway of blood flow through the heart, the physical journey that sustains life with every beat. This continuous flow is what keeps our tissues alive, our organs functioning, and our metabolism running. It's a perfect example of how anatomy and physiology are beautifully intertwined, each chamber, valve, and vessel playing a critical role in the orchestration of life. As we move forward, we'll connect this flow to the phases of the cardiac cycle and understand how pressure changes and valve dynamics regulate each step. As we continue our exploration of the cardiac cycle, it's time to focus on the unsung heroes of heart function, the heart valves. These structures ensure that blood flows in one direction, preventing backflow and maintaining the efficiency of circulation. The tricuspid valve, located between the right atrium and right ventricle, has three cusps: anterior, medial, and posterior. It opens during ventricular diastole to allow blood to flow into the right ventricle. The pulmonic valve, at the exit of the right ventricle, has anterior, left, and right cusps. It opens during systole to send deoxygenated blood to the lungs via the pulmonary artery. The mitral valve, between the left atrium and left ventricle, has two cusps, anterior and posterior. It's the only bicuspid valve and plays a critical role in allowing oxygenated blood to enter the left ventricle. The aortic valve, located at the root of the aorta, has left, right, and posterior cusps. It opens during systole to deliver oxygen-rich blood to the systemic circulation. Surrounding these valves is the annulus fibrosus, a fibrous ring that provides structural support and electrical insulation between the atria and ventricles. Sequential and coordinated changes in the heart's valve integrity, which occur cyclically with electrical conduction, are collectively referred to as the cardiac cycle. These valves open and close in a precise sequence during the heart occurs in two phases, driven by pressure changes in chamber contractions, and b. the relaxation phase or diastole. Ensures that each heartbeat is not just rhythmic, a normal adult heart pumps 75 times per minute. Understanding valve anatomy is essential not only for grasping normal physiology but also for diagnosing and managing conditions like stenosis, regurgitation, and valve prolapse. Cycle of systole and diastole. These are not just passive flaps, they are dynamic, the whole responsive structures at the heart of cardiovascular health. The atrial systole must correspond with the ventricular diastole, otherwise, the atria will fail to pump their contents to the respective ventricles. Thus, atria and ventricles are beating in their own way. However, the coordination between these two independent cycles is extremely important to maintain the proper functioning of the cardiac cycle. Atrial systole, the contraction of the atria for only a short period ensures that the respective ventricles are filled. Atrial diastole, during this process, the atria either collect blood passively from the vena cava or allow it to flow freely, thereby filling the ventricles. Ventricular systole, the ventricular muscle contracts from the apex towards the base and causes blood to be pumped out through the aorta and pulmonary trunk. Ventricular diastole, the ventricular muscle relaxes from the apex towards the base and allows the heart chambers to be filled with venous return via the respective atria. As it appears from the discussion till now that there are four distinct phases in the pumping activity of the heart. These four phases appear sequentially in the cardiac cycle. Once there is inflow so that there is increase in volume. Then there is a phase when the pressure is built that follows the outflow phase. Again, there is a low-pressure phase that continuing to the inflow. These four phases appear in the cardiac cycle sequentially and in a coordinated fashion. The electrical activities of the myocardium and coordinated functions of the relevant valves, as already discussed, are very crucial in maintaining the performances of the cardiac cycle. With the change in heart rate, the duration of these phases may vary, however, the sequence and coordination between the phases are well maintained. Let's consider the events of the cardiac cycle. We have already understood that the atrial and ventricular events are running parallelly. However, for the ease of learning, we shall consider the atrial events and ventricular events one by one. Please note that the duration of each events mentioned here are based on total 0.8 seconds duration of cardiac cycle for an average heart rate of 75 beats per minute. First, to list the atrial events, there are only two major atrial events during a single atrial cycle, the atrial systole for 0.1 seconds and the atrial diastole for 0.7 seconds. Sometimes, the atrial systole is further divided into dynamic and adynamic phase, however, that is of little significance. Next, to list the ventricular events during a single cardiac cycle, 0.3 seconds are spent on ventricular systole. It has a short isovolumetric contraction phase for 0.05 seconds, then a rapid ejection phase of 0.1 seconds followed by slow ejection phase of 0.15 seconds. In case of ventricular diastole phase, there is a quick protodiastole phase of 0.04 seconds prior to isovolumetric relaxation phase of 0.06 seconds. With the opening of atrioventricular valves, the first rapid filling phase starts and continued for about 0.1 seconds. Then there is reduced filling phase for 0.2 seconds followed by the last rapid filling phase for 0.1 seconds. Thus, the ventricular diastole phase lasts for total 0.5 seconds. As it is seen here, both the atrial events and ventricular events are totaling individually. Volume and pressure changes in the atria during the atrial cycle are very nominal. Just to emphasize, the behaviors of each phases are not absolute ventricles. These are approximated values only for an ideal cardiac cycle. During ventricular systole, they act as a reservoir, and during atrial systole, they actively pump some amount of blood to the ventricle. Thus, only during systole, there will be some minor changes in the intraatrial pressure, left atrium 7 to 8 mm of mercury and right atrium 4 to 6 mm of mercury. However, the pressure is easily distributed because of the open atrioventricular valves and valveless opening of the great veins and pulmonary veins. In the atrial pressure curve, 3 waves of positive pressure are observed, named A, C, and V. The A wave is formed by contraction of the atrial muscle, whereas the C and V waves are formed during diastole of the atria. The C wave is formed by bulging of closed atrioventricular valves towards the atrial side at the onset of ventricular systole, and the slow V wave is formed during the end of ventricular systole due to accumulation of blood, as the atrioventricular valves are still closed. As emphasized again and again, the ventricular and atrial events are running parallelly. However, highly precise coordination is maintained between the two sequences of events. Understanding this concept is very important to learn the events within the heart during the cardiac cycle. Now we shall identify the phases or cardiac cycle events, particularly the ventricular events on the timescale. Please note that how the phases are placed on the timescale so that the sequence of events can be easy to understand and remember. Starting with the isovolumetric contraction phase, 0.5 seconds is marked. Rapid ejection phase is marked for 0.1 seconds. Then the slow ejection phase is marked for 0.15 seconds. Collectively, the 0.3 seconds are marked for ventricular systole. Now, for the ventricular diastole. First, we are marking the protodiastole, a little less than the half of the 0.1 seconds to indicate the 0.04 seconds of protodiastole. Then, rest of the 0.1 seconds is marked for isovolumetric relaxation, so it is roughly 0.06 seconds. Now, 0.1 seconds for the first rapid filling phase. Next, 0.2 seconds for the slow filling phase. And, finally 0.1 seconds of the last rapid filling phase that is equal to the 0.1 second of the atrial systole phase. Now we have distributed both the 0.8 seconds of atrial and ventricular cycles into their designated phases. Continuing with the events of cardiac cycle, the phases of ventricular events can be linked with the heart sounds, that is the closure and opening of heart valves. The onset of ventricular systole is marked with the closure of atrioventricular valves, and as you now know, that is the beginning of isovolumetric contraction. The phase lasts till the semilunar valves open. Then the contraction phase continued and ejection of blood from the ventricles occur. Similarly, closure of semilunar valves indicate the onset of isovolumetric relaxation phase. This is also indicated by the second heart sound, as we shall see later. The isovolumetric relaxation phase continued till the atrioventricular valves open. Thus the diastolic phase continued with filling of blood into the ventricles till the atrioventricular valves close. Heart sounds are good indicator of cardiac cycle events. The time elapsed from the first heart sound to the second heart sound is the systole phase, and the time from the second heart sound to next first heart sound is the diastole phase. However, the phonocardiograms show 4 heart sounds. As we understand by now, the closure of atrioventricular valves and semilunar valves are related to the first heart sound and second heart sound, respectively. The third heart sound and fourth heart sounds are produced by the rushing of blood in first and last rapid filling phases, respectively. We shall discuss the details of heart sound at the end. The volume and pressure of both ventricles change remarkably during different phases of ventricular events. To understand the pressure changes within the ventricles, we shall examine the events happening in each phase of the ventricular systole. Using the timeline already prepared, first phase is the last rapid filling phase or the atrial systole. Only nominal changes in pressure is observed during this phase of both left and right ventricle. The ventricular systole sets in with the closure of atrioventricular valves. Now the ventricles are two closed chambers as the semilunar valves are still closed. The constriction of the ventricular muscles leading to isovolumetric contraction phase, resulting in a steep rise in the intraventricular pressure. This rise will continue till the semilunar valves are open. In the case of the left ventricle, the aortic valve opens at approximately 80 mm of mercury. In contrast, the pulmonary valve in the right ventricle opens at approximately 25 mm of mercury. Both, 1. Elasticity, in turn, the resistance of the aorta, and 2. Volume of blood remaining before the aortic arch are responsible for this requirement of high pressure to open the aortic valve. However, because of the difference in thickness of myocardium, the time required to create 80 mm of mercury pressure by the left ventricle is almost the same as the time required to develop 25 mm of mercury pressure by the right ventricle. With the opening of the semilunar valves, the blood can be expelled from the ventricle. Thus, pressure continues to rise, albeit slowly. Simultaneously, the ventricles continue to contract. This indicates the rapid ejection phase. During the slow ejection phase, the pressure continues to rise, and the volume continues to decrease. However, both processes occur at a slower pace. Towards the end of systole, after the attainment, contraction of muscle is almost complete, but the relaxation is yet to start, of maximum pressure, 120 mm of mercury for left ventricle and 25 mm of mercury for right ventricle, when there is no pressure gradient between the ventricles and their respective outlets, aorta or pulmonary trunk. Even then, blood continues to go out because of momentum it gained during systole. This phase of the cardiac cycle is called protodiastole. Because of this reversal of pressure gradient, the blood in the ventricular outlets tends to come back into respective ventricles, leading to closure of the semilunar valves. Now, production of the second semilunar valves, the ventricles again behave like closed chambers. During the isovolumetric relaxation phase, there will be a steep fall in the ventricular pressures in both left and right ventricles. When the pressure in each ventricle become less than the respective atrium, the atrioventricular valves will open, and this will end the isovolumetric relaxation phase. The filling of ventricles will be initiated, and as the ventricular muscles are relaxed, the incoming volume of blood will be accommodated by the ventricles without much change in pressure. Change in aortic pressure during the cardiac cycle is of particularly important. The aortic pressure will be changing along with the left ventricular pressure. However, closure of the semilunar valve will dissociate it from that during the diastolic phase. Hence, the arterial diastolic pressure is maintained at 80 mm of mercury, even though pressure in the left ventricle will be nearing zero during the diastolic phase of the left ventricle. Once we are confident with the pressure changes in the ventricles during the phases of cardiac cycle, we not delve into how the changes in ventricular volume corresponds to these changes in pressure. Interestingly, though there were quite large difference in the pressures of right and left ventricles, the volume changes are equal in both ventricles. As we have already understood, the last rapid filling phase of ventricular diastole is because of the atrial systole, thus, there will be increase in ventricular volume. After this, the isovolumetric contraction phase of ventricular systole starts with the closure of atrioventricular valves. During this phase, the ventricles behave like a closed chamber, so there is no change in volume during this part of ventricular systole. With the opening of semilunar valves, there will be sudden rush of blood into the respective outlets, marking the onset of rapid ejection phase of ventricular systole. During this phase, about 2/3 of the total ejected blood is pumped out the ventricles. Then the ventricles enter into the slow ejection phase with slower pumping of blood out of the ventricles for around 0.15 seconds. Less amount of blood also slowly moves out of the ventricles during the protodiastole phase. Then the closure of semilunar valves, as already discussed during the pressure changes discussion, mark the end of ventricular systole and initiation of isovolumetric relaxation phase of ventricular diastole. Like earlier, there will be no change in ventricular volume during this isovolumetric phase also. With the opening of atrioventricular valves, the first rapid filling phase starts and good amount of blood rushed into the ventricle for about 0.1 seconds. Then the incoming blood continues slowly for another 0.2 seconds during the slow filling phase of ventricular diastole. This finally continues to the last rapid filling phase and complete the cardiac cycle. The final blood volumes reached before the initiation of ventricular systole, the isovolumetric contraction phase, is called the end diastolic volume, and the final blood volumes reached before the isovolumetric relaxation phase is called end systolic volume. Normally the EDVs and ESVs are almost equal for both ventricles. The difference between the EDV and ESV is the Stokes volume, means the amount of blood pumped out of the ventricles in each cycle. It is worthy to mention here that the observed concurring changes in volumes is because of the series connections of the two parallel loops of circulatory circuitry. With this prior knowledge of pressure and volume changes in different parts of the heart, we can make a composite diagram of all these changes on the same timeline so that the relationship between these changes can be well understood, and we can comprehend the events happening in the heart during various sequential phases of the cardiac cycle.
First, we are plotting the aortic pressure curve. Now the ventricular pressure curves. Next follows the ventricular volume curves. Let's plot the atrial pressure curves. For better understanding, we are plotting the recordings of electrocardiogram and phonocardiogram with the same timeline. Collectively, this picture is well known as Vigas diagram after Dr. Carl J. Vigas. Please note that the diagram presented here is an incomplete one as we have not included the y-axis for these plots. Let us check the relationship between ventricular pressure and ventricular volume as it has some applied implication in health and disease conditions. With the change in heart rate, venous return, Stokes volume during different physical and mental activities, there is likely possible changes in the time frame of the duration of phases of cardiac cycle as well as changes in input and or output volumes. Hence, understanding the relationship of pressure and volume changes is specifically important to understand the cardiac functioning in health and disease. For ease of understanding, here we are considering the left ventricle only. So, this is the changes in pressure in the left ventricle during different phases of a single cardiac cycle. Same way, these are the changes in volume in the left ventricle during different phases of a single cardiac cycle. Now we would like to check the pressure changes versus volume changes in the left ventricle during phase of the same cardiac cycle. We are trying to draw a plot of the changes keeping the volume changes on the x-axis and pressure changes on the y-axis. Here, we are starting from the onset of ventricular filling, that is the first rapid filling continued to slow filling phase and finally the last rapid filling phase. During this phase, The end systolic volume is increased to end diastolic volume without any significant change in the left ventricular pressure. Next, there will be ventricular systole with closure of atrioventricular valves as indicated by first heart sound. There will be isovolumetric contraction phase with no change in volume but a steep rise in pressure reaching intraventricular pressure to 80 mmHg. With the opening of aortic valve, the pumping of blood starts in the ejection phase that continue with the rise of pressure up to 120 mmHg and again stops when the pressure falls to below 80 mmHg. During this time, the ventricular volume reduces from the end diastolic volume to end systolic volume, pumping the stroke volume into the aorta. Then with the closure of aortic valves, the isovolumetric relaxation phase starts and there will be steep fall in the left ventricular pressure without any change in its volume. The phase continues till the pressure drops to a level so that the bicuspid valve opens. These changes in pressure and volume continues with each cardia cycle repeated sequentially. Next, we would like to see the pressure-volume loop in the context of tension curves produced by the left ventricular muscle. As you can observe, the loop is fitted properly within the systolic pressure curve and diastolic pressure curve. The systolic pressure curve is active tension developed by the cardiac muscle during systole, whereas the diastolic pressure curve is passive tension developed by the cardiac muscle during diastole. At any specific volume, the difference between these two pressure curves is the actual pressure developed by the cardiac muscle at that volume. This is part of the Frank-Starling law. First heart sound. Cause AV valve closure. Sound character, loud and low pitch, 30 to 80 Hz. Duration, relatively longer, 0.1-0.17 s. Best heard, mitral and tricuspid area. Mechanical correlation, onset of ventricular systole. Electrical correlation, R wave of ECG. Second heart sound. Cause, closure of semilunar valves. Sound character, sharp and high pitch, 150 to 200 Hz. Duration, relatively shorter, 0.1 to 0.14 seconds. Best heard, aortic and pulmonary area. Mechanical correlation, onset of ventricular diastole. Electrical correlation, T wave of ECG. Third heart sound. Cause, vibration of the cardiac walls during the first rapid filling phase. Sound character, low intensity and low pitch. Duration, 0.1 seconds. Audibility, normally inaudible. Fourth heart sound. Cause, vibration of the cardiac walls during atrial systole. Sound character, low intensity and low pitch. Duration, less than 0.1 seconds. Audibility, normally inaudible. To summarize today's session, we have discussed the cardiac cycle with the following headings. Definition. Phases and their durations. Mechanical events during each phase. Atrial pressure curve. Ventricular pressure curve. Ventricular volume curve. Coordination between ventricular events and atrial events, Vigas chart. Pressure volume loop. Heart sounds. Hope you have enjoyed the session. I am sure you will be having many questions in your mind if you have followed the session attentively. Please feel free to reach me through the email address given here. I also invite you to join the next session of PSI online lecture series, which is live on PSI official YouTube channel on 4th Saturday of every month evening 7 to 8 p.m. Wish you all a happy Navratri and Dashehra in advance. Thank you for your time.